This is a talk on quantum computing for computer scientists for the first workshop on constraint solving and quantum computing at Constraint Programming 2021. My name is Ryan LaRose, and I'm a PhD candidate at Michigan State University. I'd like to acknowledge funding from a NASA Space Technology Graduate Research Fellowship. So constraint programming is not a quantum computing conference. So the goal of this talk is to develop some working knowledge, some common language about quantum computing for the talks at this workshop and beyond if you are interested. To that end, I'm not going to assume any prior background in quantum computing. This will be walking through fundamentals. I will assume basic background in linear algebra, just at the level of matrix algebra. The main takeaways from this talk will be three. You'll have an understanding of quantum circuits and as well as quantum algorithms. And then the last topic is quantum compiling. So let's get right into it with quantum circuits. The analog of this in the classical case is just a logic diagram or logic circuit. So we have at the left 2 bits labeled A and B coming in, and then some operations happened here, an AND gate and a NOT gate, and the bottom is just showing the NAND gate, which is a combination of these, and we get some output at the right. So in the quantum case, it's exactly the same, but everything sort of has the word quantum in front of it. So it looks like this. We have, this is a quantum circuit. We have at the left 2 qubits coming in. They both start in the 0 state. I could have labeled them A and B as well. And time flows from left to right, and the wires show the evolution of the qubits. So we have operations acting in the middle, and then measurements at the end. And if we break this down again, at the left, we have quantum bits, also called qubits. In the middle, we have gates, quantum gates acting on the qubits. And at the end of the computation, we perform measurements to get classical bits as output. So here, the 2 lines denote classical bits to distinguish them from quantum bits, which are the 1 line. Okay, so let's break each component down. First off was a qubit. What is a qubit? It's just a 2-dimensional wave function. I'll define a wave function in a second, but it's just a vector with 2 elements, and that's spanned by the basis, which I list here, 1, 0, and 0, 1. This notation is a physicist thing, but it's just a vector, and the notation is as follows. It's often called Dirac notation, and this straight line and then right-angled bracket is a column vector, and then whatever is on the inside of these brackets is just a label for whatever that vector is. So this is the 0 vector or the 0 states. This is the 1 vector or the 1 state. Later in the talk, and you'll often see in other places, the left-angled bracket, straight line, this is known as a bra. This is just the conjugate transpose of this guy, and this is called a ket, if I didn't mention it before. Okay, so these are vectors, or also called kets, and these are basis states for a qubit. And what's a wave function? A wave function is just a vector that has unit norm. So using this basis, I can write a qubit as alpha 0 plus beta 1. And in order for it to be a wave function, we want it to have unit norm, which means that alpha squared plus beta squared, mod alpha squared plus mod beta squared is 1. Okay, and the reason that is because we use wave functions to define probability distributions. So the probability of measuring the qubit in the 0 state is given by mod alpha squared, and for the 1 state, it's mod beta squared. This is known as Born's rule. So what's the purpose of wave functions if we just get probability distributions out of them? The reason is that wave functions can have constructive and destructive interference. So elements of wave functions are called amplitudes. So these are just components of the vector, the amplitudes, and these are allowed to be positive, negative, or even complex numbers. And because of that, if you sum them up, you can have positive and a negative in the summation, and that can go to 0. So that's destructive interference. And they both can be positive, summed together, and that's constructive interference. So a common picture of that is waves on the surface of a body of water, as shown here. So there's areas of constructive interference, areas of destructive interference. So that's one qubit. What about if we have multiple of them? So the way these combine, the space of a multipartite quantum system is by the tensor product. So you take the tensor product of all the constituent spaces. I won't formally define the tensor product, but here's an example at least. So suppose we have two qubits, one belongs to Alice. Alice's qubit is psi sub a, and it's in the state alpha 0 plus beta 1. And then Bob has another qubit. Bob's qubit is the state psi b, which is gamma 0 plus delta 1. So now if we want to look at the joint system of Alice and Bob, then it's the tensor products of both of their qubits. So that's on the left here, psi a tensor product psi b. And an example of evaluating this is I just substitute what these in. So this is Alice's qubit, this is Bob's qubit. So that's just the definition. And now to do the tensor product, it's linear across the summation. So I can distribute, and I get alpha gamma 0 0 as the first term. So I take alpha 0 gamma 0, and that gives me this one. Second term, alpha 0 delta 1, that's this guy, and so on for all the terms that you see. If this looks a little bit mysterious, don't fret, you're in good company. The first time you see this, it can be a little weird. I would recommend this blog post to demystify the tensor product. There's a lot of good examples and background and help build intuition. For the purpose of this talk, I at least wanted to mention that and show an example, and this is what we'll need for analyzing the example circuit. Okay, so that's qubits. The next element in our quantum circuits were gates. So what's the story with gates? All a quantum gate is a unitary matrix. I'll remind you that a unitary matrix is one which satisfies this equation. Dagger is again conjugate transpose. So the conjugate transpose of the matrix is the inverse. The reason we want that is to preserve the norm of a wave function. So if I take u and I apply it to some wave function psi that does have unit norm, then I look at the norm of it and I get psi u dagger u psi. And then here you see u dagger u dagger is the inverse, so this becomes identity. And then I just get psi psi, and this is 1 because psi is a wave function. So unitary gates preserve the norm of wave functions or vectors. Two examples of unitary gates, unitary matrices as gates. One is the Hadamard gate. This is one that we had in our circuit. So this is a single qubit gate, which means it's a 2x2 matrix. And it has matrix elements that you see here, 1, 1, 1, minus 1. As a circuit, we represent these things as boxes with some symbol. Often the symbol is just the same symbol as the matrix, so H here. Acting on the 0 state, this is useful notation that we'll use. H acting on the 0 state is just the first column of this matrix, which we can write as 0 plus 1 over square root of 2. So Hadamard will create an equal superposition of the two computational basis states, 0 and 1. Another example of a quantum gate, a 2-qubit gate, is the C0 gate. C0, short for controlled not. You see the matrix elements here, and what this does in words is it acts on 2 qubits. So that's why there's 2 lines here, 2-qubit wires. And it will flip the state of the second qubit, that's the bottom one here, conditional on the first qubit being in the 1 state. So what's an example of that? If I feed in the state 0, 0 here, then A is in the state 0, so the second bit doesn't flip, and I get out 0, 0. So that's the first column of this matrix. If we move to the third column, then we get that if I feed in the state 1, 0. So because A is now in the state 1, I do flip the bottom qubit, and I end up in 1, 1. And that's the third row of this matrix that you see here. And the same argument applies to the other rows. Okay, so that's quantum gates. We're 2/3 of the way there for the circuit. The last thing is measurements. Measurements go as follows. We represent them by these symbols again in the circuit. And I'll restrict to projective measurements for this talk. A projective measurement is a set of positive Hermitian operators labeled P sub m, such that if you add them all together, you get the identity matrix. So that's the completeness condition. And also, if we want them to be projective measurements, they need to be orthogonal. So that's what this equation is saying here. With measurements, the probability of getting a particular result m, so m is the index that labels these things, is given by psi p sub m psi. The last thing to mention is that after you measure the states, the final wave function will be in the state proportional to Pm acting on psi. The denominator here, square root of P of m, is just for normalization. Okay, that can be a little abstract. Let's see an example of this with a particular set of projective measurements. And we'll use what we normally use, which is computational basis measurements in a circuit. So here the projectors are given as follows. P0 is 0, 0. This is a column vector into a row vector. So this is the outer product. And that evaluates to a matrix, 2x2 matrix, which has these elements here. And similarly, the second projector is outer product 1, 1. And you get this matrix here. So it's easy to see that these add together to give identity. Just 1, 1 along the diagonal. And you can also convince yourself that they are orthogonal. So this is indeed a set of projective measurements. Now, if I want to know if I have the canonical qubit wave function, alpha 0 plus beta 1, then the probability of measuring 0 is, again, as per the last slide, given by psi p0 psi. And if you take that and work it out, then you get mod alpha squared. Similar argument, similar story for probability of getting 1, you get mod beta squared. And this is exactly the rule that I stated before when I mentioned that wave functions define probability distributions. So this is just taken from a previous slide. Okay, so that's all of the elements of quantum circuits. Now let's go through and analyze mathematically the example circuit that I showed. So how does this go? We start in the 0 state on both qubits. And so I have written that here. So 0, 0. And if there's no tensor product, then you just assume that one's there. It's common to leave it out in this notation. Okay, so we go left to right. We march through the circuit. The next thing we see is a Hadamard gate acting on the first qubit. So we now know what that means. We defined before the Hadamard gate takes the 0 state into an equal superposition, 0 plus 1 over the square root of 2. And then nothing happened to the second qubit. There's no gate there, or the identity gate. And so that just stays here. Okay, the next gate is the C naught. Before we get there, I'll make it a little easier to analyze. And so I'll just use the distributive property of the tensor product to write this as 0, 0 plus 1, 0. So again, it's 0, 0, and then 1, 0 for the second term. Now the C naught gate, and we know how this operates. It's a linear operator. Quantum gates are unitary matrices. Matrices are linear operators. And so I can evaluate each of the terms separately. So the first term, the first qubit is in the state 0. That's what the control is on. And so nothing happens to the second qubit. So this stays in the state 0, 0. Now for the second state, I have 1, 0. The control is on the first qubit. And since this is 1, we will flip the second qubit here. So 1, 0 becomes 1, 1. That's an example of analyzing a quantum circuit. Start in the 0, 0 state. That's the canonical starting state. Apply some gates. And in this case, we end up with the state 1 over root 2, 0, 0 plus 1, 1. Now, I chose this state to mention briefly one other interesting quantum mechanical phenomena, which is entanglement. So before that, if just to mention quickly, if you want to play around with quantum circuits, I would recommend this website. That's how I created this circuit diagram, and it will allow you to simulate them, sort of a drag and drop simulator, and you can get some more intuition for what's going on in quantum circuits. Okay, but back to this state, it's an entangled state. So what does that mean? Here's just a copy of the state. We're thinking of it as a joint state on Alice and Bob's qubits. And I claim that this cannot be written as a tensor product of two individual states. So it cannot be written as some state of Alice's qubit, tensor product, some state of Bob's qubit. And this is true, you can prove it. I won't do it now, but whenever this happens, we say that the state is entangled. This is a sort of brute force definition. There's more elegant formulations of this, but this is the intuition. If you cannot write it as a tensor product of two states, then that is an entangled state. Entangled states have useful properties and are used as resources in algorithms and other protocols. One more bit of vocabulary: if a state is not entangled, we say that that state is separable. Okay, so we've analyzed an example quantum circuit mathematically. We can also analyze this by actually executing it on a quantum computer. So in particular, IBM allows us to do this over the cloud. And if you navigate to this website, you may have to create an account, but eventually you'll get to some screen that looks like this. And we see a quantum circuit diagram here with a bunch of gates that we can throw in at the top. So this is, again, a drag and drop simulator. So let's prepare the Bell state that I showed in the circuit. To do that, I need a Hadamard gate and then a C0 gate. And then I need to tell the computer which measurements to do. So I want to measure both qubits. As we argued, the final state of this is 0, 0 plus 1, 1. So the only states that I should measure, the only bit strings that I should measure are 0, 0, and 1, 1. So we can take that and we can send it to some device. I'll pick the first one here just arbitrarily, and I can click run. And we'll see our job was sent to that device. So depending on how many people are trying to use the quantum computer at whatever time you run this, you may have to wait a few minutes. For the talk, I've went ahead and run that previously. And so we can see the results here. And what we see is that you do indeed measure 0, 0, and 1, 1 most of the time, but not all of the time. In practice, these devices aren't perfect. So there are some errors that occur, and we may measure 0, 1 or 1, 0 a few times, even though in principle, if it was perfect, we should have never measured those. So this is the full histogram of results. And this is an example of running a quantum circuit on a superconducting qubit computer. So back to the slides. I'll skip this next one, which was just a summary of what I showed. And just to mention briefly, as an aside, if you're interested more in the what really happens in superconducting qubit quantum computers at sort of a lower level, what the physics is, then I would recommend this reference, Quantum Engineer's Guide to Superconducting Qubits, and you can find it at this link on the archive here. Okay, now that we know quantum circuits, we have some language to talk about quantum algorithms. And I want to show quickly just an example of one quantum algorithm, arguably the simplest one, the first one, to get some intuition of how these properties that I use, that I mentioned, constructive interference and destructive interference, are used to solve problems. So this is how this algorithm goes. First, what's the problem? We want to consider a function of a single bit. So f inputs 1 bit and it outputs 1 bit. There are 2 inputs and 2 outputs, so there are a total of 4 functions that act on a single bit. And I've listed them here as an example. The first function always outputs 0, no matter what the input is. The second function always outputs 1, no matter what the input is. And these top 2 functions, let's call them constant. We'll call them constant because the output is the same without respect to the input. The other two functions, f3 and f4, let's call balanced. Balanced meaning that there's an equal number or a balanced numbers of 0 and 1 in the output. Okay, so we can separate these four possible functions into these two classes. And then the problem is, given an arbitrary single bit function, so one of these guys, one of f1 through f4, we want to determine if that function is constant or balanced. So whether it's one of the red guys or one of the blue guys. And the way we do that is by making queries to the function f. A query is I send in a bit of input and it gets evaluated, and then I get the output bit. So it's not hard to argue, in the classical case, this will take at least two queries, right? Each bit is independent. I have to send in both bits in order to determine whether the function is constant or balanced. In the quantum case, we'll be able to do it with one query, and I'll show you how that works. First, what is the analog of the query in the quantum case? We'll use the following, which is sometimes called the phase query. So Q sub f is the query. It'll act on a quantum state now, x, where x is either 0 or 1. And it'll do something that doesn't even make sense in the classical case. It will apply a phase to the qubit, where the phase is given by -1 to the power f of x. If this looks a little suspicious or worries you, then I'll just mention briefly that this is the same as the above oracle, the above query, which might be a little bit more natural. So here Q sub f acting on x is just f of x. So maybe that's more natural to think about. These two are completely equivalent, though. There's a simple trick that you can do to take this query into this phase type query. Okay, so with that, we have our query now, and I claim that this quantum circuit here, this algorithm, will tell us whether f is constant or balanced, and there's only one query to the function f here. So how does that work? We have all the tools to analyze this now. We start in the 0 state, as we always do, and then I apply a Hadamard gate. Hadamard gate takes the 0 state to 0 plus 1, and I'm going to omit the normalization factor just for ease of notation. And then after the Hadamard gate, we apply the query, and this is the phase query, so it'll take 0 and do -1 to the f of 0 plus -1 to the f of 1 on the 1 state. Okay, we're almost done. One more Hadamard gate. The Hadamard gate, we just apply to each term individually. It'll give us a 0 plus 1 here, and then a 0 minus 1 here. Hadamard on the 1 state is 0 minus 1. And if you take that and arrange it in a way that's useful, then you'll get the following. So the amplitude of the 0 state will be this guy, and the amplitude of the 1 state will be this guy. So what does this do for us? Why is this useful? Let's think about it as follows. I'll copy the state here. This is the same state, final state of the circuit. And let's suppose that f of 0 is equal to f of 1. If f of 0 is equal to f of 1, then it's not too hard to see that these terms, both these terms in the square bracket, will have the same sign, either positive or negative. And these terms will have the opposite sign, one positive, one negative. So this amplitude, the coefficient of the 1 state, will have destructive interference. It will go to 0. And the amplitude of the 0 state will have constructive interference, and so we'll get some state that's proportional to 0. And why is that useful? Well, at the end of the circuit, we make a measurement. So if we measure 0, then we know that f of 0 was f of 1. In other words, the function was constant. Same argument, similar argument holds if f of 0 is not f of 1. You can show that the final state here will be the 1 state. So here's the picture that I showed before, constructive, destructive interference. That's an example of how this is used in this algorithm. And the punchline is that we solved the problem using only one query to f, whereas in the classical case, we needed two queries. So this is the quantum algorithm described in the paper by Deutsch and Joza, Rapid Solution of Problems by Quantum Computation in, I believe, 1992. And if you want to learn more about this, I encourage you to follow this link. and there will be some more about the Deutsch-Jose algorithm there. Okay, so that problem was an example quantum algorithm, and it seemed artificial because it was artificial, but there's a sort of direct line of reasoning from Deutsch to the Bernstein-Vazirani algorithm. This is Umesh Vazirani. After that, Simon's algorithm as well. I can find a picture for that though. Ultimately to Shor's algorithm. And I've not heard someone argue that Shor's algorithm is solving an artificial problem. So this is his paper in Abstracts, Polynomial Time Quantum Algorithms for Prime Factorization and Discrete Logs. So using the same principles, and to reiterate that, I want to show you a high-level picture for the circuit of Shor's algorithm. And it's very similar in structure to the simple Deutsch-Jose single qubit algorithm that we just analyzed. So you start out by Hadamarding everything. You make a query to some function, and then you kind of do a Hadamard. This is a quantum Fourier transform, and then you measure. So it's the same exact principle that Shor's algorithm works on, and constructive destructive interference is at the heart of it. If you want to know more about Shor's algorithm, I encourage you to follow this tutorial, or there's a lot of other good online material. And if you're interested in knowing what other quantum algorithms exist, what problems can they solve, what are they good for, I encourage you to check out the Quantum Algorithm Zoo, which has a lot of problems, algorithms, and references so that you can learn more. Okay, so that will conclude the first part of quantum algorithms. And now I want to get into quantum compiling. So this is the previous image that I showed about the device that I ran the 2-qubit Bell state circuit on one of IBM's computers. And I have a confession to make. I said that I ran the circuit Hadamard C0, but in reality, this device can't implement a Hadamard gate. So if you look closely here, the basis gates, which means the gates this device can implement, are C naught, identity, Z rotation, squared or not, and the not gate. There's no Hadamard there. So what happened? I told it to run a Hadamard gates, but that's not one of the gates it can do. So what happened under the hood was that it took the Hadamard gate, here's the circuit, and it compiled it, meaning that it translated that gate into a sequence of operations that the computer knows how to implement, can actually implement. And so this is a simple example, but an insightful one. And this is the main idea of quantum compiling. We can define it as the task of expressing a high-level quantum circuit in low-level operations that a given device can perform. So that includes both the basis gates, as well as the couplings, so which qubits that you can do 2-qubit gates between. That's represented by the edges here. So this is a 5-qubit device, 0, 1, 2, 3, 4. And if I wanted to do a 2-qubit gate between 0 and 3, qubits 0 and 3, I couldn't directly do that. I would have to do some intermediary gates between 0, 1 and 1, 3 in order to do that. So that's an example of compiling, a simple one. What's another example, just to show you how important this is? This is now just compiling a circuit with 2 single qubit gates and 1 3-qubit gate. This is known as a Toffoli gate. And here we see the number of C0 gates, 2-qubit gates that this takes to implement. So 2-qubit gates are noisy. You want to have as few 2-qubit gates as possible. So compiler is not just translating the gates. One task of it is also doing it in a sort of optimal way. And that's important for near-term algorithms, especially, and really every algorithm. You want to have the circuit run with as few gates as possible. Okay, so an important result in quantum compiling, just to mention it quickly, is the Solovay-Kitaev theorem. So this sort of gives you the scaling in terms of the accuracy that you want for doing compiling. And it goes as follows. So let G be an instruction set for some d-dimensional unitary. So this is the basis gates. And we give it as input and desired accuracy epsilon. Then the result is that we can compile for any unitary u a sequence of gates from G, which has length of order log 1 over epsilon raised to some constant c, which is at most 4 and I think between 2 and 4, such that this compiled sequence is epsilon close to the original unitary. So that's an important result, and it sort of sets the stage, sort of what's possible for compiling. If you're more interested in that, I would encourage you to check out this reference, the Solovay-Kitaev algorithm, which is available on arXiv at this link here. And in practice, when you do compiling, there's sort of these tricks or identities that you use. Just to give you an idea, one useful result is that an arbitrary 2-qubit unitary can be expressed as a quantum circuit with at most 3 C0 gates, and the single qubit rotations you see here. So that's a useful result or identity, and these are the kind of things that compilers in practice will use. To give you another idea of the importance of compiling right now, IBM ran a challenge where one of the exercises was exactly compiling. So people were given an arbitrary unitary U, and they wanted to get a sequence of single qubit rotations and C0 gates within epsilon accuracy of that. And the cost of this was given by 10 times the number of C0 gates plus the number of single qubit gates. And there were over 1,800, approximately 1,800 participants in this challenge. And the top score achieved a cost of 45. And they did that by an approach that's described here, which used a sort of machine learning approach to compiling at this reference. And this bottom link here is a link to the GitHub repository for the Qiskit challenge that I took the screenshot of this from. So you can check that out if you're interested. Machine learning is one approach to compiling. There's other approaches. One of them is mapping the problem to temporal planning. And so I just wanted to briefly mention this work by some folks in the NASA group. And what they did there was, again, frame the problem of compiling in the language of temporal planning, and then use some state-of-the-art programs for doing temporal planning and scheduling in order to do the compilation there. So if you're interested in compiling with this approach, I encourage you to check out this paper and some of the follow-up work that they did. Okay, nearing the end of the talk now, we've covered quantum circuits, quantum algorithms, and quantum compiling. I want to get back into quantum algorithms with one more example of a sort of class of algorithms that you may hear spoken about at this conference, as well as other venues. And this is commonly called the class of variational algorithms or variational quantum algorithms. This is a figure which describes the process at a high level that I took from this arXiv paper. And the only difference from before is that we still have some quantum circuit. Maybe there's multiple of them. And the key difference is that we now take the quantum gates and we parameterize them by some set of angles. So one or more or all, some subset of the gates will have a variational parameter. And so the final wave function that we prepare will be parameterized by that as well. And so we use a quantum computer, we send in some angles, and we use that to evaluate a cost function. This is shown, I guess, sort of by this neural network here. And this cost function may look like this if there are 2 parameters. And we send in some particular values of the angles theta, and we land somewhere on this landscape. And then we use the classical computer in conjunction to adjust these parameters to try to find the minimum or maybe maximum of this landscape. So sort of typical optimization procedure, but the portion of evaluating the cost function, or at least some of it, is done by a quantum computer. An example of this is we can have the cost given some Hamiltonian, which is a particular observable, which gives the energy of the system, and a single qubit wave function parameterized by one angle. I can sweep the angles from 0 to 2 pi. So this is the angle theta here, and then this is the cost on the y-axis, the vertical axis. And we see the single parameter landscape that it produces. Looks like a sine curve or a cosine curve. And the blue one is on a typical quantum computer, or an example quantum computer. The other two are on simulators, so classical computers mimicking a quantum computer. And I show this to have you give an example of what a simple landscape can look like, and also to mention that these variational algorithms can have some robustness properties or resilience to noise, in that if we just want the location of the optimal parameter, then that occurs more or less at the same spot on the blue curve, the real quantum computer, as on the simulator. Although there is this shift, this bias vertically, the sort of argmin is at the same spot. So that can be one useful feature of variational algorithms, and one reason why they are a somewhat popular approach to implementing quantum algorithms right now. One particular algorithm, variational algorithm, is known as the quantum approximate optimization algorithm, or QAOA. And the conventional way this is framed is in terms of max cut. So max cut, I may not need to describe to this audience, but you're given some graph, a set of nodes and edges, and you want to partition the nodes into two sets, which are distinguished as white and black here, such that the sum of the weights between the two sets is maximized. So that's known as a cut, and you want to find the maximum cut. So this is a standard problem in graph theory. And how do we formulate this as a problem that we can use a quantum computer to solve? The first step is to write down an energy of the system, or a Hamiltonian. And the Hamiltonian looks as follows. So z sub I and z sub j here are representing nodes I and j. And so these can have values +1 or -1. And so if they're both +1 or they're both -1, if they're in the same set or they have the same sign, then this will square to identity, and identity minus that will give 0. So that's exactly what you want with max cut. They evaluate, you attribute nothing to the cost if they're in the same set. If they're in different sets, then you'll get a minus sign here. And then so with the 1/2, that'll give you 1 times the weight of wij. And to make it truly quantum, I guess, these are not just spins or bits anymore. This is now the Pauli Z operator. So that has eigenvalues +1 and -1. So these are matrices, not just values +1 and -1. Okay, so that's the energy. And then what the QAOA says to do is to prepare a variational wave function that looks as follows. I start, this should be the plus state actually. I start in the plus state, and then I first do a cost Hamiltonian on it. So that's H sub C here. This should be first. I apologize, I have the terms in the wrong order. So the first unitary you implement is the exponential of this. All of these commute, so you can do a sequence of 2 qubit gates. And then the second unitary that you do is known as a mixer Hamiltonian. And there's multiple choices that you could do here, but one sort of standard one is a sum of Pauli x's on each qubit. And so this is easier to visualize in a circuit. So I start in the all plus state. I first do that evolved by the Hamiltonian H sub C, and then I do the mixer Hamiltonian, and that's one layer, which I showed here. And then you can repeat this for a certain number of layers. So that's what the circuit diagram is showing here. If you want to have more background in this or you're interested, I encourage you to check out this tutorial by Penny Lane, which is a good one for the QAOA. And I took this image here from that tutorial as well. The last thing to say about the QAOA, just explaining it a little bit more, is it's the same approach as any variational algorithm. So now that you have this ansatz wave function prepared by this circuit here, the first thing you do is you optimize over these parameters theta to get the maximum of the energy here. And once you do that, the last step is where you get the output from. So you then prepare using the optimal angles theta opt, the ansatz wave function, psi of theta opt, and then you measure that in the computational basis, and that will give you a sequence of bit strings like we've seen before. And so the bit strings, for example, 000, 011, all the way up to 111, they occur with some probabilities. And then the ones with the most probabilities, those are sort of what you take to be your answer. And what do the bits mean? Again, the bits in the formulation of the problem, 0 would correspond to one class of nodes, for example, the white ones here, and then 1 would correspond to the other class of nodes, for example, this one here. So as a final output, if this was the most common bit string, that's telling you that if this was, say, 101, then that would be a 3-node graph, and it would tell you to put the outer two, the first and the third nodes in one class and the middle node in the other class. And that's sort of the final answer, how you get an answer out of this quantum algorithm. Okay, so let me summarize now. We talked about quantum circuits, and the building blocks were qubits, quantum gates, and measurements. We use quantum circuits to describe quantum algorithms. I showed us one simple example of one, and then I talked about a few others, notably a variational algorithm, which can be used to solve combinatorial optimization problems, at least in an approximate sense. And then the last thing that I mentioned was quantum compiling. So this was the task of taking a high-level quantum circuit and expressing those same operations into the low-level gates that a particular computer can implement. So that's a quick but brief tour of quantum computing with the relevant topics, I think, for this conference. There's other areas in quantum information science outside quantum computing. Some of them I list here. These are all sort of Googleable terms. If you're interested, I encourage you to check out more. And that will conclude my introductory talk on quantum computing for computer scientists. I hope you find this useful, and I hope you find the rest of the talks at the first workshop on constraint solving and quantum computing interesting as well. So thank you for your attention. I will leave you with a quote by Charlie Bennett, who says, "We shouldn't be asking, where do quantum speedups come from? We should say, all computers are quantum. Some of them just have too many eavesdroppers. And instead ask, where do classical slowdowns come from?"